One more example we take here. Kf for water is 1.86 Kelvin kg per mole. Kf, the molar depression constant, shows per mole of the substance in 1 kg solvent how much depression is observed in the freezing point. Kf, it is 1.86 for water. It depends on the solvents. How many grams of ethylene glycol must be added to 1 kg water to get the freezing point of the solution lowered to minus 2.86 degrees Celsius. So here, the freezing point depression and the freezing point depression constant, the two are taken there. The depression in freezing point is the colligative property, and this colligative property is given with a very simple relation delta Tf, freezing point depression, is directly proportional to molality, or we put it as delta Tf equal to Kf, a constant, into molality. That is giving us all the required values. Delta Tf equal to Kf into molality. And about this molality, you spread the molality term. It goes with weight of the solute divided by molar mass of solute into 1 is the factor for the solvent in terms of kg, and it is the weight of the solvent. That is the formula. How much of ethylene glycol should be added means we have to calculate the weight of the solute. So, weight of the solute here, if I introduce weight of the solute, this becomes equal to delta Tf into molar mass of solute into weight of the solvent divided by the Kf. Into 1. Very simple. Introduce the value delta Tf. Make no mistake, it is not minus 2.8 degrees Celsius, because minus 2.8 degrees Celsius is the freezing point of the solution. But the depression in the freezing point, that is from 0 to minus 2.8, means the depression magnitude works out to be 2.8. Hence, introduce the 2.8 here, not minus 2.8, and molecular mass of solute. For that, we are assisted with the formula. It gives 62 into the weight of the solvent. Weight of the solvent is 1 kg divided by, it is 1.86. You can easily calculate with the calculator, and the answer that we get here is 93. And we shall confirm it here as it is 62. Ignoring this decimal, it becomes 186. 62 divided by 186 means it is 3. But when the decimal is here, it will be 0.03. 2.8 divided by 0.03 comes roughly about 93. And that is the option number 4. In the next, one more new information we can have here as far as the molar masses are concerned, that is the abnormal molar masses. Pertaining to that, an example, 20 gram of an acid dissolved in 50 grams of benzene, the Kf for the benzene is 1.72 Kelvin kg per mole. The freezing point depression is given, that is 2 Kelvin. That means 20 gram of the solute is given here, 50 gram of benzene, weight of the solvent is given, and Kf is given 1.72 Kelvin kg per mole. Freezing point depression delta Tf is given. From these, we have to calculate the Van't-Hoff factor. Now look, if we are to calculate in this formula, we will be calculating the molecular mass of solute. This molecular mass is to be calculated. It is calculated from the experimental value. And when the formula is given here, from that formula we will be getting the formula mass. And this formula mass is the normal molar mass. Experimental value of the molar mass is abnormal molar mass. Therefore, do one thing, you will be getting the molecular mass here, normal molar mass, divide it by the experimental molar mass, abnormal molar mass. So, the value gives you the Van't-Hoff factor. Do this calculation on your own and you will have the first option, that is 0.5. Van't-Hoff factor is 0.5. It clearly shows that this substance is undergoing association in the solvents. Therefore, its Van't-Hoff factor is less than 1. So far, we have discussed the two topics, solids and the solutions. Few questions have been taken for the interpretation. Hope you have enjoyed these questions and also got an approach towards these multiple choice questions. So many are there in the reference books. Please make use of them and approach them. Find a better way of getting the correct options in the shorter time. Do well, and my wishes will always be with you. And so friends, I am Velar Gaudar, wishing you all the best.